Hello students, in this session we will discuss about equivalence classes and sparse matrices. Now, an equivalence class means it is a collection of equivalence relation partitions. So here mainly we focus on equivalence relation. Now, let me take any relation R over a set S, then the relation is said to be equivalence relation if and only if the relation is reflexive, symmetric and transitive. So simply referred as RST. Now, what is meant by reflexive, symmetric and transitive operations? Here observe, let an element X belongs to the set S, then the pair X comma X belongs to the relation R. Now this property is referred as a reflexive property. Then symmetric, let X comma Y belongs to S. If X is related to Y, then Y is related to X. Now observe here, if X related to Y implies Y also relates to X. Now this property is known as symmetric property. Transitive, let X, Y and Z belongs to S. If X relates to Y and Y is related to Z implies X is related to Z, then it is referred as transitive property. So if the relation satisfies these three properties, then it is referred as equivalence relation. So when we place such type of equivalence relations, now the class is treated as equivalence class. Okay. Now, to generate such type of equivalence classes, let us consider a generalized algorithm. Here, to design this algorithm, now it consists two phases. So in first phase, first we identify equivalence pair and then the pair is added and stored in the result. In second phase, the process starts with 1 and find all pairs that are related as 1 comma j. Okay. Now, values of 1 and j are placed in the same class. Okay, so in such a way it is possible to identify equivalence classes. Now observe this algorithm. Void equivalence is a generalized wave. First one, initialization. Now is a repetition process while there are no more pairs. First read the next pair as I comma j. Process the pair. Now close while loop. Now output point of view, initialize the output, do open brace, output a new equivalence class and curly brace while not done. Now here implementation part completed. Now it shows a general view to identify equivalence classes. Okay. Now this concept, sparse matrix. So a sparse matrix is a matrix representation in which number of zero elements is greater than the number of non-zero elements. Now it shows one example. So in this matrix it consists 5 rows and 6 columns. Here the matrix consists 5 into 6, 30 elements, in which the number of non-zero elements are 1, 2, 3, 4, 5, 6, and number of zero elements are 24 elements. So here number of zero elements is greater than the number of non-zero elements, hence it is an example for sparse matrix. Now, a sparse matrix can be represented using arrays and linked list. So at this stage, let us consider a sparse matrix representation with linked list. Here two formats are valid. In first format, in linked point of view, it consists nodes. So here each node is divided into different fields like I, J, row link, column link, and data parts. So here I represents row value, J represents column value, row link is a pointer variable that points to next node in the same row, call link is a pointer variable that consists address of the next node in the same column, and data part stores information part of the element. In general, we place non-zero elements. Format 2. So in this format, each node is divided into 4 fields like row, column, data, and link parts. So row represents the index of the row where the non-zero element is located. Column represents index of the column where the non-zero element is located. Data part consists non-zero element at the specific index value, and link part stores address of the next node. Now observe this example. Assume this one sparse matrix. For this, the linked representation should be in this format. Now observe here 4 non-zero elements are available. Hence we place 4 nodes, and each node is divided into 4 parts. Now observe here the first non-zero element is available in row 0, column 2. Hence row value 0, column value 2, and non-zero element is 18. This one link part that points to next node. Next non-zero element, row 1, column 1. So 1, 1, non-zero element is 46. Link part. Next non-zero element, row 1, column 3. So 1, 3, 32. Next element, here non-zero element, row 2, column 2. So row 2, column 2, and non-zero element is 24. Okay. Thank you one and all.